Hello and welcome back to Real Analysis. And first, many thanks to all the nice supporters on Steady or PayPal. Now in this video today you will get to know some important continuous functions. Some of them are so important that they are often called elementary functions. Indeed, all of them we will consider again later when we differentiate and integrate. Hence, let's immediately start with the most important one, the exponential function. We shorten the name with exp and the domain is the whole real number line. And we have already learned in the former video that it is defined by a series. Namely, we have x to the power k divided by k factorial. And now you might already know, at the point x is equal to 1, we find the so-called Euler's number. Also, it's possible to show that this number can be defined by another sequence. Namely by the limit 1 plus 1 over n to the power n, which is roughly 2.718. Now, this exponential function shouldn't be new to you, because we have already discussed it in part 22. There we have shown the fundamental multiplicative identity for the exponential function, which translates the addition inside into a multiplication outside. And because we have this property, we can immediately explain the name exponential for this function. For example, if we have x of 2, we can write this as x of 1 plus 1, which is by our fundamental multiplicative identity here exactly x of 1 times x of 1. So it's Euler's number squared. So you see the left here and the right hand side are the same. And indeed we can show that in general the exponential function x of x is exactly Euler's number to the power x. Therefore the name makes sense because we can rewrite the function such that we have the exponent here. And of course we can show even more properties of this important function here. The first part might not surprise you, the exponential function is a continuous function. So it's continuous at all points in R. Then the next property is that this function is at all points increasing. More concretely, we would say the exponential function is strictly monotonically increasing. Which simply means if we look at 2 points x and y, where y is greater than x, then also the values fulfill the same inequality. So x of y is greater than x of x. In addition, we can also say what happens in the limits x to infinity and x to minus infinity. For plus infinity, we exceed all bounds, therefore we go to plus infinity. However, for minus infinity it's different, because we stay positive the whole time, we reach 0 in the limit. Okay, so these are the important properties you really should remember for the exponential function. Now, one important conclusion here is what we will need for the next example. Namely, now you are able to show if we change the codomain to 0 infinity, so the interval of the positive numbers, then we get a bijective map. Indeed, that's not hard to show when you know all the other things here. And of course, now you already know, a bijective map has an inverse map. And this inverse is what we usually call the logarithm function. So you see, this is a simple definition, and then we can ask the question, what are the properties of the logarithm function? And of course, not so surprising, we can deduce a lot of properties from the exponential function. So maybe let's look at the graphs to see what we already have. So in blue you see the graph of the exponential function, and then we reflect it where the mirror line is this diagonal. Here please recall, this reflecting follows immediately by the definition of the graph and the inverse function. Hence here in red you find the graph of the logarithm function. Now what we see is that the logarithm function is also strictly monotonically increasing, and it should still be continuous. Indeed, showing these two things is a very good exercise. First you show the increasing part, and then you use the epsilon-delta criterion to show the continuity. Okay, however the most important property for the logarithm function follows immediately from the fundamental multiplicative identity for the exponential function. Okay, now because the logarithm function is the inverse function, this identity goes the other way around. So the product inside gets translated to the sum outside. Okay, I can tell you, this identity is very important, so please remember it. Now with this we go to our next examples, which are polynomials. For them I don't have to tell you a lot because you already know them. The important part here is the domain of a polynomial is the whole real number line. And defined is it by giving finitely many coefficients a. And in the case that the last one, am here, is non-zero, we say that the polynomial has degree m. As a reminder, we have already showed that the polynomials are continuous functions. So nothing new here, but we need to know the polynomials to define the next class of examples. Here, please recall, for a polynomial, an important ingredient was that we have a highest power m here. If we don't want to have that, we get something we call a power series. In fact, this is a very general term where we already know one example. Namely, the exponential function from above was defined using a power series. Now in general, a power series does not need to be defined on the whole real number line. So we could have a smaller domain d. However, otherwise it looks like a polynomial where we have coefficients ak here, but now we could have infinitely many. In other words, for each sequence ak, we get out a function we call a power series. In this case, the domain of definition is given by all the points x in R that satisfy that this series is indeed a convergent one. And of course, you already know a lot of criteria you can use here to check for convergence. Okay, let's immediately discuss a very famous example here, which means we fix a special sequence ak. Let's start the sequence with the 0th member, which should be 0. And then I want 1, but let's write it as 1 divided by 1 factorial. Then afterwards comes 0 again, and then minus 1 divided by 3 factorial. Then not so surprising, we have 0 again, and then 1 divided by 5 factorial. Then 0 and then minus 1 divided by 7 factorial. Okay, with this I think you see what the whole rule is and that you can continue it. And now this sequence gives us a power series we usually call sine of x. Also, it's not hard to check that the whole real number line is the domain d. Indeed, a lot of common functions can be defined with such a power series. And for this reason I give you here a general result. Now for any power series given with coefficients ak, you find a maximal radius r, where also infinity as a symbol is possible, which indeed would be the best case scenario. Now this maximal radius fulfills that the open interval from minus r to r lies completely in the domain d. Now I can also tell you we immediately get that the power series is a continuous function on this interval. So in the best case scenario, like for the sine function, we have a continuous function defined on the whole real number line. Now even better for the theorem, we have a formula to calculate this number r. Indeed, this comes out of the root criterion for series, therefore we can calculate the lim sup of the kth root of the absolute value of ak. And this gives us the number 1 over r. And here in this case for 0 and infinity we use this symbolic calculation. Using this we have this formula in general. Okay, now this nice formula is often called the Cauchy-Hadamard theorem. With this I would say we've learned a lot today and we can start with derivatives in the next video. Therefore, I hope I see you there and have a nice day. Bye!